Hey guys, and welcome back to another video. Today we're going to be talking about wave propagation. I pulled this question from a fall 2019 midterm, from the third midterm. Let's go ahead and take a look at it. So it's always good to highlight exactly what you're given in the question first. We're given a frequency of 1592 megahertz. We see that the wave is propagating based off this equation that we're given in milliamps per meters. So now let's go ahead and write down that equation. We're told that H naught is equal to y hat. Y hat means that the magnetic field is propagating via the y direction, omega t plus 40x minus 30z plus 0.1 pi. Okay, so let's take a look at what we're given so far. We have here y hat. So we're told that the magnetic field is propagating via the y direction. We're given a magnitude of 10. We're missing an omega. So if we solve for that right now, what is omega? Omega is equal to 2 pi times the frequency. The frequency was given to us. That was 2 pi times 1592 megahertz. So that's times 10 to the 6th power. That comes out to 10 to the 10th power. What else do we have? We have k. So this, we can derive a k vector from what we're given. Now remember, the k vector values are always the opposite sign. That's negative 40x hat plus 30 z hat. Why is that? Well, you have to remember that the equation is originally derived from cosine omega t minus k dot r. So if we see here, this negative sign, if distributed to all values of k, will make all positives negatives and all negatives positives. It will switch the sign. That's why we always give the k vectors the opposite sign. Now, from this k vector, we also can find a value of k. K is simply the square root of the squared sum of the values. That's 40 squared plus 30 squared, square rooted. That equals 50, because it's a simple 3, 4, 5 triangle. Now let's see what else we have. Well, we don't have much, but we have omega and we have a value of k. So how can we relate the two together? Well, v, the velocity of the wave, is omega over k. If we input their values, that's 10 to the 10th power over 50. That is equal to 2 times 10 to the 8th power. Because this is a wave essentially travels at the speed of light, unless it's traveling through something. So the velocity is 2 times 10 to the 8th power. But we could also say that the velocity is equal to the speed of light hindered by the refractive index. The refractive index of an object, of a material. We know that c is a constant 3 times 10 to the 8th power. That's the speed of light. If we rearrange this to find n, we get the speed of light, 3 times 10 to the 8th power, over 2 times 10 to the 8th power, the velocity of the wave. That comes out to a refractive index of 1.5. What do we do with that refractive index? Well, eta comes in handy. Eta is defined as eta naught over n, the refractive index. You're probably asking what eta is. Eta is a wave impedance. Where does eta naught come from? Well, eta naught comes from the square root of mu naught, which is the permeability of free space, over epsilon naught, which is the permittivity of free space, both of which are constants. mu naught is 4 pi times 10 to the negative 7. Epsilon naught is 1 over 36 pi times 10 to the negative 9. It's equal to 120 pi, which is equal to 377. Now remember, eta is impedance, therefore the units for it is ohms. Now we can solve for our eta. Eta naught is always a constant 377 ohms. 377 over the refractive index that we just found earlier using the velocity. That's 1.5. This equals 251. Great. Now what else can we do? Well, we want to relate the electric field with the magnetic field. We want to relate the magnitudes of the electric field to the magnetic field. So the equation we have for that is the electric field over the magnetic field equals eta, the wave impedance. This simplifies out to, because we're looking for the electric field, that's E naught equals eta H naught, which is values that we have, that's 251 times, now we do have H naught. H naught is this magnitude here. That is the magnitude of the wave. So H naught is 10. Or is it? Remember, we're working in milliamps per meter. What we want, ideally, is amps per meter. So this 10 milliamps per meter is really 0.01 amps per meter. If that's the case, our value ends up being 2.51. Now we have a magnitude for the magnetic field. Great. Now let's try and graph everything on our coordinate plane. So I like to use my k vector to figure out what my axes will be. So the k vector has x and z in it, so I will choose x and z as my axes. With x and z being my axes, we know that the y direction goes into the page. The positive y direction is into the page. Now we have a k direction. The k direction is given by negative 40x, 1, 2, 3, 4, and positive 30z. So our k direction looks like this. We also know the direction of the magnetic field. We know that the magnetic field magnitude is 10 in the y hat direction. This means that H, the magnetic field, is also going into the page. Now this is where we start to use our right-hand techniques. Now, some important information to know is that K is perpendicular to E and likewise perpendicular to H. We can simplify this. The magnetic field and electric field are always in phase. Basically, if you have either the electric field or the magnetic field equations, you can find one using the other because they have the same phase information. Also, we can simplify this into k hat direction is equal to E cross H. Now that's crucial information. This defines our right-hand rule. So if you look at the top right of my screen, I provided a right-hand rule guide. A cross B, your thumb will be your k direction, always. your pointer finger, your index finger, points in the direction of the electric field, while your middle finger always points in the direction of the magnetic field. So if that's the case, if we point our thumb in the direction of K, and we point our middle finger in the direction of Y, your pointer finger should be pointing in this direction. That is our electric field direction. How do we define that? Remember that K and E are perpendicular. That means there's a 90-degree angle between these two. That being said, that means that the electric field's direction is positive 30 x hat plus 40 z hat. So let's take everything and put it together. The equation for the electric field is in the 30 x hat plus 40 z hat direction that we just found. We divide that by the K value, which was 50. We multiply by the magnitude of the electric field, which we found was 2.51. And remember, the electric field and magnetic field share the same phase information because they are in phase. Therefore, we can copy the exact equation from the original question. Sine omega t, omega we found was 10 to the 10th power t, that's plus 40x minus 30z plus 0.1 pi. If we simplify this out, we have 1.5 x hat plus 2z hat direction sine 10 to the 10th t. Remember that these waves are time dependent, plus 40x minus 30z plus 0.1 pi. And are we finished? No. Remember, the original equation was given in milliamps per meters, but we converted the magnitude into amps per meter. This means that our electric field will be in volts per meter units. And that is our equation for the electric field. So, to reiterate, knowing that the electric field and the magnetic field are in phase, in that they share the same phase information, it was very easy to find the electric field equation using the magnetic field equation. We also used the right-hand rule to help determine the direction of the electric field. With that being said, I quite enjoy these kinds of problems. They're really fun to do, and they're pretty quick to understand. I hope you enjoyed this video. I hope it helps you out, and I'll see you in the next one.